Moving on, we now have a number of people to introduce from RWTH Aachen, talked by Alexandra Radl, a scientific research assistant at the Institute for Advanced Mining Technologies, who is jumping in for Professor Elisabeth Klausen, the director of the Institute. We also have Ksenia Milicevic, hopefully I'm pronouncing this right, Milicevic-Neumann, Senior Research Advisor at the IME Institute, Process Metallurgy and Metal Recycling, who is replacing Professor Bernd Friedrich, head of the Institute, because they also have parallel sessions, and Professor Hermann Wotruba, head of the Department of Mineral Processing. But as Professor Klausen and Professor Friedrich have parallel responsibilities, they did shoot a video which we can see now.
Welcome, my name is Elisabeth Klausen and I'm the director of the Institute for Advanced Mining Technologies. At the Institute for Advanced Mining Technologies at RWTH Aachen University, we are doing in research, teaching and transfer, we are contributing to safe, efficient and sustainable raw materials extraction by the automation and digitalization of mining machinery and processes.
My name is Bernd Friedrich. I'm head of the Institute for Process Metallurgy in the Aachen University, and being part of the faculty of Georesources and Materials Technology. Here in Aachen we joined forces since many years, from mining, from processing into extraction of the metals from our terrestrial deposits. And this talk we give you today will show you how we want to transfer this know-how into lunar and space resource technology in the future. I hope that you will enjoy our talk in the next minutes.
We are convinced that providing best possible input materials for each process step will lead to efficient production of oxygen, but also to high quality metal materials, which then can be used for further applications.
Therefore, it's necessary to follow a holistic approach that takes into account mining, processing and beneficiation. Starting with selective mining, which is represented by the AMT, we are aiming at providing the best possible blend based on the original material of the deposit. The deposit conditions, which are normally and generally characterized by a high variability.
Subsequently, mineral processing is done by the AMR.
Once we receive the concentrates from Professor Wotruba, it is our task to recover metals and oxygen from this material. And we are using especially technology calling Mosari technique, which combines metallothermic reduction and electrolytic reduction in order to optimize the zero waste utilization of this very expensive material from the moon. And we will present that in our talk in a very detailed manner.
And now we learn more about our experiences and ideas together with Alexandra Radl and Ksenia Neumann.
Enjoy the presentation, take care and Glück auf!
It's wonderful to have that video with them, even though they are occupied elsewhere right now. So, as they said, we can directly transfer to the talk with Alexandra, Ksenia and Professor Hermann.
So, thanks a lot. I hope everyone can hear me loud and clear and you can see my presentation.
Definitely can see you.
So, that's great. So, hello everyone, my name is Alexandra Radl. I'm a research assistant and PhD student at the Institute for Advanced Mining Technologies. My research focuses on the characterization of mineral raw materials in mining environments. And furthermore, I'm responsible for coordinating the AMT's space-related activities. So together with Professor Wotruba from the Unit of Mineral Processing and Ms. Neumann from the IME, I will now give you an insight into our experiences. But first of all, I'd like to start with a short introduction about the Institute for Advanced Mining Technologies. In research, education and transfer, the Institute stands for safe, efficient and responsible raw materials extraction by the automation and digitalization of mining machinery and processes. So from our background, we are a Terrestrial Mining Institute, and our research focuses on the application of ruggedized sensors in the mining environment, including the generation of data and the processing of data, using, for example, signal and image processing. The resulting smart services contribute to the automation of machines and processes in various areas of the raw materials extraction. But coming back to space and our integrated conceptual design for the production of oxygen and structural materials from lunar regolith. As the ANT's role in this concept is the mining process, I want to start with some thoughts about the extraction of regolith. So although the regolith covers the entire lunar surface, this will be a highly complex process. Firstly, we all know there are extreme environmental conditions. We have the really thin lunar atmosphere, the duration of the lunar day and night, extreme temperatures and temperature fluctuations, as well as the radiation, which will have an impact on our mining machinery. And of course, we have to deal with the low gravity. But when thinking about lunar mining, it is also important to consider our raw material, the lunar regolith, which has a really heterogeneous composition and further challenging characteristics as it's, for example, fine and dusty. And this leads us to the following requirements for lunar mining machinery and methods. So this list is not really detailed and shall only give you a really general overview. For lunar mining, we need innovative methods, for example, to deal with the lower gravity. And when thinking about terrestrial mining, we all have those big and heavy machines in mind. But instead, our process has to be small and efficient, for example, to reduce launch costs and effectively mine in space. And therefore, we also need a process that works highly autonomous. Furthermore, to cope with the environmental challenges, we have to think about robust machinery and consider a reduced energy demand. And this leads us to the idea of selective mining, which also requires to include material characterization. But before I'm coming to this, I want to come back to Earth. So here on Earth, we have an increasing world population, which is closely linked to an increasing demand for mineral raw materials. And even today, these raw materials are mainly provided by mineral deposits. At the same time, increasing safety and environmental requirements, as well as sinking raw material concentrations and more complex deposits, which also includes more extreme environmental conditions, have made the extraction of raw materials more difficult. And important elements for meeting these challenges are the increasing automation of processes and the development of innovative concepts in order to make the excavation of raw materials more efficient. And so we see we need innovative and highly autonomous mining concepts and methods for both space mining and terrestrial mining applications. And even though we at the ANT have only little experience in the area of space mining, we have extensive experience in the automation and digitalization of terrestrial mining machines and processes, as I want to show you with this slide. As you can see, for us there are three main topics, which are the autonomous mine, the green mine, and the safe mine. And within these topics, we have contributed to various projects as the automation of the rock cutting process, including material characterization for selectively extracting the resources, but also to projects in the field of localization, mapping, and navigation. And when it comes to safe mine, we have contributed to projects for adaptive mine ventilation, as well as object and person recognition. And last but not least, we have contributed to projects in the field of deep-sea mining, and therefore made our first steps in some kind of a non-terrestrial mining environment. And we are convinced that the space domain is multidisciplinary and needs interaction among the experts of different disciplines to face a complex future project in ISRU. And therefore, we believe we can contribute to the development, especially in the area of space resources extraction, but to learn and to adapt technologies for improving mining here on Earth as well. And this brings me back to the topic of selective mining. I already told you that it's not enough to just focus on the extraction. We have to keep the whole process in mind, and therefore also take into account the heterogeneous composition of the regolith. So for certain applications or processes, defined characteristics of the regolith are required or at least helpful. And when it comes to this, we should think about selective mining. But what means selective extraction or selective mining, and why should we follow this approach? I want to start with what happens when we're not following this approach. Then we would just extract all of the regolith at a certain site. Of course, this sounds pretty easy as there's a lot of regolith on the lunar surface, but this will lead to higher mass flows, lower concentrations of our valuable resource, and therefore make the following steps, which is in our case the processing and the metallurgy, more difficult. If we now instead follow the approach of selective mining, we will only extract the regolith where we already have a slightly higher concentration of our valuable resource, which will lead to more efficient mining process and even has a positive impact on the following processes. And therefore, we do not only need to know the requirement of our subsequent processes, but also need to know where we can find our valuable resource in rich concentrations, and therefore detect or identify the material before and during the mining process. So we can summarize this as a local condition. And in order to get this knowledge, we need to include sensor technologies into our mining machinery to continuously characterize the material. And with this, we want to extract the material in such a way that we can provide the required quantity of the right quality at the right place and time, in the best case with a minimum of effort and energy. So to sum it up, because the metallurgy has to be highly efficient, there are highest requirements for processing, which can be achieved the best if the input material already has good concentrations of our valuable resource. So we have highest requirements for the mining process too. And therefore, even though there's a lot of regolith on the moon, we should focus on selective mining to have an efficient mining process and give an iron-rich regolith to processing to later have a good concentrate for the metallurgy. And with this, I would like to hand over to Professor Wotruba, who will now present you the challenges of processing in space.
Thanks a lot. Yes, I will talk about mineral processing in space. As a mineral processing engineer, I'm in between the mining guys and the metallurgists, and the same on Earth, the same will happen on the moon. Please, can you show the next slide? Mineral processing, what is it? It's the treatment of raw materials, mineral materials, with the objective to produce usable products. So mineral processing does not change the chemical properties of minerals, opposite to metallurgy. So we are a part of the process line of raw materials. Starts with the mining, and then comes mineral processing, and then we can have sometimes a direct use of this material, what we produce, for example, for building materials. Or we have another step in between, which is metallurgy. So we have mining, mineral processing, metallurgy, and then use. Next slide, please. Yeah, what are our goals there? We want to use the minerals on the moon and produce oxygen, water, metals, and construction materials. So 4 different products we want to produce. And we will have the first step, which is the selective mining of the raw material, of the raw ore. And then follows the first step of mineral processing. Probably we can produce already aggregates for construction, whatever that is. And then we have a concentrate or prepared feed for the next step, which is the extraction or metallurgy to produce oxygen, water, fuel, metals, etc. Yes, so what is our raw material? In the first step, we will concentrate on the regolith. The regolith is very abundant on the moon. We have different types of regolith, the Highlands regolith, the Mare regolith, and the composition is slightly different. This is here an example of the Mare regolith. We have about 30% of pyroxene, 30% of glass-rich basalt. We have about 20% of anorthosite. We have about 11% of olivine, and we have 4.3%, around 4% of ilmenite. So ilmenite is our main target mineral. The properties of the regolith, it's loose, so we don't have to blast it, we don't have to crush it, we don't have to mill it. It's already fine. It's very fine. It's finer than 1 millimeter, but it goes down to 10 or even less microns. So we definitely need no crushing and need no grinding for this material, which is good because crushing and grinding machines are usually heavy machines, which also need a lot of energy. So we don't need that place. We might have some coarse rocks in that material, which might block our further processing steps. So we need a kind of screening to screen off these coarse rocks. And our target mineral, as I said, is ilmenite. Ilmenite is an iron titanium oxide, and it's magnetic, or it has magnetic properties. You can extract it by magnetic forces. It's a conductor, so we can use electrostatic separation. It has probably a specific particle size in the regolith, so we can even concentrate it, upgrade it by screening or classification. It has also a higher density than the other minerals, but as we have no very little gravity, density will be not the main property to extract it. So what can we do? First, we have to have a kind of screening classification, so separation by grain size. On the Earth, we have mainly gravity, which drives a fine material through a screen. We have to find out what happens in space when we have very little gravity. Does this normal conventional screening processes still work? Or do we have probably centrifugal systems, which are also available? And we replace the missing gravity by centrifugal force. So this might help to separate the fines from the coarse. The screening machines are not so heavy compared to crushing or grinding machines. There are lightweight machines possible, made from aluminum, magnesium, titanium, or plastic, reinforced plastic. So we can have a lightweight, robust screening equipment on the moon. Next slide, please. Then the question is, how do we concentrate the ilmenite? So what kind of separation methods do we have? I think the preferred method would be magnetic separation. We could use drum separator, crossbar separators, disc separators. There are different types of magnetic separators, and they all work in the way that the magnetic forces do attract the magnetic particles, and they don't attract the non-magnetic particles, so we can separate them. Another option would be electrostatic separation. This makes use of the different conductive parameters of material. The ilmenite is definitely a conductor, and okay, the chromite, which is also present, is also a conductor, but the other minerals are non-conductors. So we might use electrostatic forces to separate the ilmenite from the rest of the regolith. And also here, lightweight machines are possible. Please, next slide. There's a lot of questions I have. We have some samples, but not many from the moon. So at the moment, we have this information that ilmenite content on Lunar Mare regolith is about 4%. But on Earth, this would be a grade of deposit which is already used in beach sand deposits. But there are deposits on Earth which have a much higher ilmenite content. It goes until more than 90% ilmenite in the rock. So these high-grade deposits exist. I don't know if there are similar deposits on the moon. So it's a question of exploration. For the regolith, also the question about particle sizes. Our dry concentration processes, they have reduced efficiency if the material gets very fine. On the Earth, no problem, we will use water when it's getting fine. We will not have the possibility to use water. So we have to manage it completely dry. And we have the question of agglomerates and how does it behave on the moon with very little gravity and very fine material. So the question is, are the results when we process a similar composed ilmenite ore, are the results from Earth transferable to the moon? As I said, reduced gravity, reduced or no atmosphere, extreme changing of temperature of feed material, probably pre-charged particles, which will have by the solar wind, which will have an effect on the electrostatic separation. We have some handling questions. How do we transport the material? What happens to the dust what happens with dust anyway? Does it settle down, or how fast? And what can we do to get the dust out of the way? You know, on the Earth we can just use a dust extraction system, which works we suck the dust and we filter it. But if there's no atmosphere, how will we do it? So many questions about how our good experiences with ilmenite ore from the Earth. I already made two process developments for ilmenite hard rock mines, and I also worked a lot with ilmenite, alluvial ilmenite, but still I don't know really if I can transfer this to the moon. We will have the chance in Germany to do experiments at reduced gravity. We have such two gravity towers here, no gravity towers in Germany, where we might be able to do experiments. I'm looking forward to it. Thanks a lot.
So I think I will continue. Can you hear me?
Yes, we can hear you.
And also construction workers, my apologies. So hi, my name is Xenia, and I will guide you through the last stage of our RWTH Aachen journey toward oxygen and structural materials production. Next slide, please. First of all, I would like to introduce our institute and activities. One of them is recycling, which can be applicable for space resources. Actually, we had one project regarding space debris. Next one is metal refining. I will not talk about it today, but definitely important if we want to produce high purity metals. Process design is something that follows every process in our house, let's say. But today our focus will be on special processes, molten salt electrolysis, and metallothermic reduction. Our institute has about 60 employees, scientific and non-scientific staff, equally divided, and we have around 30 student workers that support us in everyday work. So, next slide, sorry. It's very disturbing, this background noise, my apologies. So something about molten salt electrolysis and the fundamentals. So as the name says, it is the molten salt electrolyte, which is typically chloride or fluoride based, and then we put inside a regolith that is oxide based, and with the help of the direct current we dissociate these oxides onto metallic cation that reduces at the cathode, and oxygen ion is oxidized at the anode. Next one, or actually, yeah. So why is it important that we have very specific oxide concentration inside the melt? Is because if we don't have enough of oxides, we will dissociate the electrolyte. And if we have too much, then we will form the slime, and it will lead to reduced efficiency of the process. Next one. So I want to say that we have more than 10 years of expertise in process development of the molten salt electrolysis. So we have fully automated process in-house. How it looks like, you can see here the electrolysis cell that is placed into the furnace. Below that is actually the source of electricity, you cannot see it. And then we have in situ off-gas detection. So we detect all the gases coming out of the process. And that everything is connected to the process controller that triggers the feeding device in order to have continuous process. Next one. One more technology used for the reduction is metallothermic reduction. So with this technology, we also can reduce the oxides or the ilmenite. But the difference is this is exothermic reaction and self-starting after initial ignition. On the right side, you can see the reactors where we placed the raw material before the process and during the process. So quite a firework, let's say. Next one. Yeah, so based on these two technologies, molten salt electrolysis and metallothermic reduction, we have created the zero waste concept that we call MOSARI. How it looks like? Well, the first step is electrolysis of the regolith in fluoride-based electrolyte. So within this process, we have the oxygen evolution and as well master alloy deposition. Why we chose to use the fluorides is because they have a lower vapor pressure than the chlorides. As you have heard in many talks, typically is used FFC process in fluorides. And we have a direct separation of product from electrolyte, and with it we have a prevention of material loss. On the right side, you can see a few thermochemical modeling diagrams that actually can present us which phases we have during the process or deposition. Next one. So the next step would be the metallothermic reduction of the beneficiated regolith with the previously obtained metals from the electrolysis. So we're using those metals to reduce the beneficiated regolith. So we have the upgrading of the master alloy, and we have the selective reduction of iron titanium with some amount of silicon alloy. And the beauty of this concept is that we have this acidic product that is iron titanium depleted regolith that can be returned into electrolysis cell. And this slag may be used as construction material for 3D printing and so on. And herewith we have developed the zero waste process. Next one. Yeah, so here you can actually see the schematic depiction of our concept, and I am very, very happy to announce that we have actually registered a patent for it. So if I want to summarize our journey of RWTH Aachen, or actually IME, so we have developed the concept for zero waste production of oxygen and functional materials. Patent is registered. The initial calculations and modelings are performed. Equipment and know-how is available, and the tests are ongoing, as well as the continuous optimization of equipment and process for space application. So this is something, so you can see actually our journey, how we start from the selective mining through beneficiation, and at the end the reduction in order to achieve the high quality metals. So merci beaucoup, and if you have any more questions, you can contact us directly. Thank you.
Thank you very much, all three of you. And of course for the video introduction as well. Again, as always, we've got a large conversation going on online. Hopefully you've been keeping track of most of it. Have you any questions for our speakers?
Yes, there's a lot of activity going on in the chats. I'm almost sorry for the people that are sitting in the room because they can't see it. Our previous speakers are very active, but I managed to filter out some of the questions for our speakers now. Also big thanks from my side for your talk. Let's start with the first question for Alexandra, I would think. Urs Polker from the Bergakademie Freiberg is asking, the regolith is a powder type material, or as Jerry Sanders corrected, a kind of shattered material. How do you adopt, for example, selective mining technologies to this material?
So, of course, this will be really difficult and a challenge. What we are thinking about when we are talking about selective mining is, so Professor Wotruba told us about the concentrations of the ilmenite and the regolith, and this is the average. So we might have some areas where the concentration is slightly higher. So with this, we are doing the selective extraction. Of course, it won't be perfect, and we will have some minerals we don't actually need, but it makes it more easy for the processing to do the work and give a good concentrate for the metallurgy. I hope this answers the question.
I can probably also answer a little bit to that. The AMT is working a lot with the sensors directly on the mining machinery, and it constantly monitors the quality of the phase. And the idea is to have sensors which detect titanium and iron at the phase, and then when you mine it, decide if this material which is actually mined is dumped or goes into the processing. And every percent of higher ilmenite content or grade in the material will help to improve the efficiency of the separation process later. This is the concept.
Thank you. Actually, the next questions I have is for Professor Wotruba, as we have you already on screen. So it was again Jerry Sanders, who is very active today. His question is, besides ilmenite, have you considered creep, so potassium, rare earth elements, or phosphorus materials as a resource for consideration?
No, we didn't. At the moment, our information of the regolith is only what I gave you at that slide, and there's no other metal let's say in a concentrated form present. It's only ilmenite, it's iron, titanium metal material, and there's for sure there are traces of rare earths. They are not rare, but we didn't consider this.
Thank you for that. Last question. Unfortunately, I don't have one for Xenia, but it's again for Professor Wotruba. The regolith would be highly charged due to the solar wind, but wouldn't different regolith materials hold different surface charges? The person asking the question thinks this would actually be a plus for the use of electrostatic separation. Do you have any comment on that?
No, definitely could be. That is already pre-charged. What we have to see is how are the different minerals charged, and can we really use that for separation, or is there a homogeneous charge on all the materials? And the other question is, if we dig down deeper and remove the top layer, if this activation by the solar wind is still the same, or it is less if we go down, let's say, half meter or even deeper, and probably then the charging might be different. At the moment, I have no knowledge about that, how it behaves. If it's different deeper down, but definitely it's an interesting idea to use that pre-charging by the solar wind for electrostatic separation. Yes.
Thank you for that. So I will just close this talk by reading two comments. The first from Thorsten Dank. Very nice and clear presentation, Hermann. I see the dust still is an open point, but that's to be discussed or is already being discussed in the chat. And then a general presentation, general comment from, just a moment, Christophe Bosquillon, who's saying, great presentation of the value chain in 3 stages. Thank you and congrats for the patent.
And Christoph is another who's been very active on all of the chats over the last couple of days. So thank you for continuing to keep up your energy as well, because that gives us all great energy too here in the room and to see your correspondence online.